So this lecture is devoted to fractals. It's quite interesting geometrical objects which have many interesting features, including self-similarity. So geometric objects, one of their features that can have infinite lengths of infinite area, so it's infinite measure, I will call it. And kind of self-similarity. So let's talk about measure. So what we know how to measure length of curve given by differential function, differentiable. Function. Okay, maybe I will show it. So this is our function. Let's say E, P, X, Y, f of Y, and then we know that its length is given by integral of from A to B 1 plus derivative of y squared dx. So this was formula from mass 101 probably, and it is easy to see how it works. So we divide this curve into pieces. So these are pieces. This is a piece. So for this piece, we have here delta x, here delta y, and this delta L, length of this small piece, is square root of delta y squared plus delta x squared, so it can be approximated like this. And this can be put it like square root of 1 plus dy over dx squared times delta x, and this at the end comes to this. When we add up all of them, we get this. And so L can be found, provided, so what is here important, L can be found if dy over dx exists almost everywhere. Say for any x between A and B. But this is not always the case. So what I will show, I will give you an example of curve for which derivative dy over dx doesn't exist nowhere, not any point. And its length apparently is infinite. So this example, I will call it example, so-called Koch. It is built like this. We take segment of length 1. So we call it step 0. We start with segment of length 1. Then at step 1, we remove middle third of this. So this is 1/3, this is 1/3, and replace middle third by 2 other segments of length 1/3. So this is step 1. At step 2, we do same procedure with all 4 segments we have. What it means. So we build the curve in iterations. And at every next iteration, we replace middle third of all segments in the object by 2 new segments. Of size of removed part. Now let's count length of this curve. So this curve is shown here. This is at step 1, step 2, step 3, and so on. And it has infinite length because at step 1 length, I will put here step node where we have only 1 segment of length 1. So at step node, length is equal to 1. At step 1, length is now we have 4 segments. Each segment has length 1/3, so it's 4 times 1/3. At step 2, length is now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now we have 16 segments. Each of them has length 1/9. And we can continue at step n. We will have step n. We will have length which will be 4 to the power of n times 1/3 to the power of n. So this is number of segments. And this is size of segments. And now we can see that L, which equals to 4/3 to the power of n, tends to infinity when n tends to infinity. So length of this curve is infinite. So to characterize these strange objects like this, it's called also monster curve, we will introduce a quantity, and this quantity is called fractal dimension. So this is pretty much like dimension we know, but extended to strange cases. So what we know from geometry? We know that point has dimension 0. So it doesn't have, its length is 0, area is 0, everything is 0. So it has dimension 0. So now if we consider line, so it has length L, and line has dimension 1. Similarly, some shape, planar shape on the plane has dimension 2. And finally, if we will consider kind of three-dimensional object, something like this cone, then 3D objects have dimension 3. So what I want to do, I want to introduce kind of algorithm which would give dimensions for known objects, correct dimensions for known objects, but then we will check what kind of dimensions we will get for fractals. So what we do to measure dimensions, well, at least to check how to do this dimension. Let's consider a line. So to measure line, length of line, we use ruler. So, and we apply ruler as many times as it takes. So ruler has length epsilon, say, then ruler of length epsilon is applied n times, I will put it, so it depends on size, to cover a line. And then we can say that L can be estimated as n of epsilon times epsilon. And from here we can say that n, the function of epsilon, is, well, we can put it like this, tends to L over epsilon when epsilon tends to 0. I will put it like this, L over epsilon to the power of 1. Now assume we have a shape on the plane. Now we will cover it. Let's put it like this. So we cover all plane by small squares of size small squares. Of size epsilon. So epsilon squared is area of measuring square. Then again, so area of our object can be, we can say, tends to number of measuring squares times epsilon squared when epsilon tends to 0. So this is also can be, it's more or less intuitively clear. And from here we can say that number of boxes required to cover our planar object tends to area of planar object divided by epsilon squared, when epsilon tends to 0. So what is here important? This one, similarly for three-dimensional object, for object in space, we can use boxes, box of of size, say epsilon. So box, in fact it's cube, to cover the object, and it will be the same. So volume will be equal to number of cubes to cover this object times volume of each cube. And here we again find that number of small cubes to cover our object tends to volume of our object divided by epsilon cube, when epsilon tends to 0. So again, so here we have this cube. And now we can use this as definition of fractal dimension. There are many definitions of fractal dimensions. This particular one is called box counting dimension. The idea here is to use measuring boxes, to cover the object. And count number of required boxes, and check whether it tends to some constant times epsilon to the power of minus d, when epsilon tends to 0. And here d is dimension. So we find d by counting number of boxes, and this d will give us dimension. So let's check how to count it. So if n of epsilon tends to c times e to the power of minus dc, when epsilon tends to 0, then logarithm of n tends to logarithm of c plus dc times logarithm of 1 over epsilon, as epsilon tends to 0. And finally, from here we can find that dc equals to limit, when epsilon tends to 0, of logarithm of n minus logarithm of c divided by logarithm of 1 over epsilon. And this can be cancelled because this tends to infinity. This tends to infinity, and therefore we can cancel this. Okay. So this will be at the end limit as epsilon tends to 0 of logarithm of n over logarithm of 1 over epsilon. So this is definition of this is the definition of box counting dimension. And now we can apply it. So if we have a first case point, so we have a point. Point can be, so point on the plane, for example, we can cover it with small box. Box can be, well, we'll call it box. It could be square, could be box really. So we have a, let's consider square. Then what we find that to cover this point, we always need n equals to 1 for any epsilon. So it doesn't depend on epsilon. So therefore, dc, which equals to limit as epsilon tends to 0 of logarithm of n over logarithm of 1 over epsilon. So n is always 1, so it is 0. So this equals to 0. So dimension of point, this is dimension of a point. So if we have a straight line, say, so this straight line is easy, it would be, this curved is the same. Now we put boxes of size epsilon. So then length, what we can see that length is n times epsilon, and we can see that n is proportional to 1 over epsilon. And therefore, dc will be equal to 1. We can check it. Limit of logarithm of n over logarithm of 1 over epsilon, when epsilon tends to 0, this equals to 1. And for third case, it is the same. So now we have a geometric object on the plane. So this is a plane. Now what we can do, we can cover plane with small squares. And we will then remove all, so there are many, many squares. Remove all squares which don't cover object. So if count the squares covering object. So we can do it even easier. So what I will do, instead of considering any object, I will consider a square. Say L by L. Then we can see that number of squares which complete this will be n equals to L squared or epsilon squared or area or epsilon squared. And therefore, if we find dc, again we should use this. And this will be equal to 2. One interesting example of this fractal structure in nature was introduced like in 70s in one of the papers. So it was an example of measuring British coastline. So to measure British coastline, we can use different rulers. And then if we use ruler of size 200 kilometers, we find that length of coastline is 2,400 kilometers. If ruler is smaller, so I think here it's 50 kilometers. So anyway, so if, yeah, 50. So for 50 kilometers, length is 3,400 kilometers. And then what is climbed when, so epsilon equal to 200 kilometers. Then L is 3,400 kilometers. Epsilon is 50 kilometers. L is 3,400 kilometers. And here what is climbed is epsilon tends to 0, L tends to infinity. So because there will be smaller and smaller details to be taken into account on the of details of coastline, and this will generally mathematically it can increase length of coastline to infinity. Physically, it's not correct because these details of coastline has some physical limitations. So you can get to as small as, well, I don't know, sizes of molecules or whatever, of sands. Now let's consider examples. So let's consider examples. Example. And this example is called counter set. So we start again. So this is done in iterations. So at step 0, again, we have a segment of length 1. At step 1, it is quite similar to Koch's curve. What we do, we remove 1/3, but we don't replace it by anything. So this is 1/3, this is 1/3. Then at step 2, each of these two segments, from each of these two segments, we remove middle third. So it will be 1/9, 1/9, here 1/9, here 1/9. So if we consider length, at step 0, length is 1. At step 1, length is 2/3. At step 2, so let's put L node, L1, L2, is 2/3 squared. And at step n, Ln is 2/3 to the power of n. What we see that L is 0. L is limit of Ln when n tends to infinity. And this equals to 2/3 to the power of n when n tends to infinity. And this is 0. Now let's measure dimension of counter set. So number of boxes again at step 0. I will put it like this. Step, number of boxes. And size of box epsilon. You can call it scale. So at step 0, we have one box and length scale of length is 1. At step 1, we have 2 boxes and scale is 1/3. At step 2, we have 4 boxes, 1/3 squared. So at step n, we have 2 to the power of n boxes, 1/3 to the power of n. Or we can put it like this. 1/3 to the power. Now to find dimension, box counting dimension for counter set is equal to limit when epsilon tends to 0, logarithm of n divided by logarithm of 1/epsilon. So n is also we have logarithm of 2 to the power of n, and here since this is epsilon, so 1/epsilon it will be 3 to the power of n, so this will be logarithm of 3 to the power of n, and this is n times logarithm of 2 divided by n times logarithm of 3, which is logarithm of 2 over logarithm of 3. Anyway, so this is less than 1. So this is dimension of counter set. Next example. Is called Sharpinsky triangle. Again, at step 0, we have a triangle. Let's say size 1. At step 1, what we do, we divide this triangle into 4 pieces, 4 equilateral triangles, and remove one of them in the middle. So now half, 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 half. And at step 2, what we will do, each of remaining triangles also divided into 4 pieces and 1 piece removed. 1 piece removed in the middle. So now length of side of each triangle is 1/4. So what we have here, number of boxes and epsilon. So 1 box, epsilon equals to 1. So here we have 3 boxes, epsilon is half. Here we have each of these 3 gives 3, it's 3 squared, and it is 1/4. So now at step n, we'll have 3 to the power of n triangles, and size will be 1 over 2 to the power of n. And let's find capacity dimension or box counting dimension of Sharpinsky triangle. The capacity dimension is limit of n over 1 over epsilon, when epsilon tends to 0, and this will be equal to logarithm of 3 to the power of n divided by logarithm of 2 to the power of n. This equals to 3 logarithm of 3 over logarithm of 2. This is roughly 1.6. So what is interesting? Let's put it like, let's make some conclusions. Counter set. Length of counter set is 0. Dimension is logarithm of 2 divided by logarithm of 3, which is less than 1. So this means that it is not quite line. It is object which is which has dimension which is less than dimension of line. And now Sharpinsky triangle. Length, in fact, we can count length. Length equals to infinite. Length means perimeter is infinite. Infinite, it is not difficult to show. Area. Area eventually is 0. This is interesting. I will show these two observations. And capacity dimension is logarithm of 3 over logarithm of 2. And what we can say, DC is more than 1 and less than 2. So this is more than line and less than proper shape on this surface. So more than 1 comes more than 1 means length is more than length of line, and less than 2 means area is less than area of planar figure. Now with length is easy. Length equals to limit when epsilon tends to 0, and this was n times epsilon so this n is 3 to the power of n, and epsilon is 1 over 2 to the power of n. And we see that this is 3 over 2 to the power of n, so this is limit. When n tends to infinity, and this is infinity. So this is about length. With area is, we can check the area. So we have lots of triangles. So each area of each triangle. So this is number of triangles times area of each triangle. number of triangles is 3 to the power of n, and area of each triangle, so this is equilateral triangles with size 1 over 2 to the power of n. So this should be squared times half. You can check it, it's area of triangle. Half times sine 60 degrees. So this will be some constant times 3 over 4 to the power of n. Which tends to 0. One comment which I missed to do earlier. So here measuring box is triangle. So here what we used, number of boxes are triangles. So we not necessarily should use squares. So triangles are, but so if we would use squares, we would have the same answer, but it would be much longer procedure to prove that we have still the same fractal dimension. When we use triangles, it makes it easier because this ratio is the same on every next step. It is the same always, so it's not changing. So it is just it makes easier to calculate fractal dimension. And in fact, we're free in choosing shape of our measuring box. Okay.